All right, we are right at the start time, 2 o'clock Eastern Time. So we will begin. First off, good afternoon. I am Jason Thomas, project engineer at America Makes, and your host for today's America Makes TRX webinar series. A little background on the TRX webinar series before I introduce our speaker. As America Makes continues its mission to expand and accelerate the footprint of additive manufacturing and 3D printing, this medium, called the America Makes Technical Review and Exchange Webinar Series, was created. By creating this platform, it allows the additive manufacturing and 3D printing community to come together and share knowledge and experience with a broader community. If you or your team are interested in presenting during the TRX webinar series, there will be a link to complete the request form at the end of our series today, or you can contact the America Makes TRX webinar series administrator, Jason Thomas, directly. A few important notes before we kick off the series. At the end of the presentation, there will be an opportunity for a brief question and answer session. If during the presentation you have a question, please submit it in the Q&A space on your WebEx screen, and we will ask it during the Q&A session. We will do our best to get to all the questions. Today's webinar is on how to create advanced heat exchanger designs in nTop platform. Without further ado, it is my pleasure to introduce Mikey Vlahinos and Ryan O'Hara from nTopology. Mikey Vlahinos is a senior application engineer at nTopology with a primary focus in the aerospace and defense industries. He brings nearly a decade of CAE expertise in CAD, FEA, and CFD to the nTopology team. His work, thermal performance of minimal surface heat exchangers, was most recently presented at the SIM AM 2019 conference in Pavia, Italy, and featured analysis performed in ANSYS, CFX, and Discovery Live. Dr. Ryan O'Hara is the technical director for aerospace and defense for nTopology. He brings 20 years of military service and experience as a developmental engineer to the nTopology team. Ryan has served all over the world, leading engineers that have enabled incredible advanced material and engineering solutions through the use of composites and additive manufacturing. Most recently, he served as at the U.S. Air Force Institute of Technology, where he led over $5 million in academic research programs while standing up one of the first metal additive manufacturing labs in the U.S. Air Force. Mikey and Ryan, I will now turn it over to you and your team.
Hey, Jason, thanks for the introduction. I'm going to skip ahead a couple of slides here and let Ryan take over for a little bit, and then we'll hop into some of the heat exchanger designs that we have.
Great, thanks, Mikey. Yeah, so I just wanted to focus on a few things today. When we talk about heat exchanger designs, the focus will be on the heat exchanger design itself, but also how we can couple geometry and advanced manufacturing together in the same piece to kind of enable the next generation of heat exchangers. So one of those is we're going to focus a little bit on how we can automate and parameterize designs, and with a focus on doing this in nTop platform. Also go over a high-level view of how you can actually, by parameterizing your designs, you can use that performance-driven approach to actually enable the heat exchanger to meet the performance requirements that you want. I've seen this with many customers in the past where you're kind of doing on-demand ordering, where instead of ordering maybe a class or type of heat exchanger, maybe they actually would put in the actual requirements and the resulting part would be generated from that. And then finally, we'll talk about how we can use these heat exchangers in an application that we presented in Italy, but also in coordination with our partners at Hughes Research Laboratory, where we coupled advanced geometry, manufacturing, and materials together to enable this next generation of heat exchanger designs. Get the next slide, Mikey. Yeah, so a big question is, what is nTop platform if you haven't heard already? And fundamentally, we're just a computational modeling platform for design, simulation, and advanced manufacturing, right? And the key benefit to, or the key way we enable this is through the use of implicit geometry. So it's an alternative method to represent geometry instead of by boundary surfaces. We actually represent geometry as a sign distance field. And fundamentally, that sign distance field is an equation. So we basically wrap geometry with equations and then and take an approach to that. And when we do that, we're not limited by patches or boundary surfaces. We just represent the geometry itself by the equation. In addition to that, the use of equations allows us to take a field-driven approach to design. And this is kind of implemented kind of in the image you see below the text here, where we can actually take stress fields or distance fields or flow fields, and we can couple that to the implicit geometry, and we can manipulate the geometry to kind of do what we want. So that might be adding a lattice and then variably thicken that lattice based on areas of high stress, or maybe minimizing a lattice or some other type of infill based on the flow conditions that we want to keep, right? So we can use that geometry that surrounds us in everyday life as fields to enable our designs. And then fundamentally, we create a reusable engineering workflow, and Mikey will demonstrate how we can actually enable you to create blocks and actually reuse them in a manner that you would really like. Within our company, we've been saying we're, in addition to the computational modeling piece, that we're a tool that allows you to make new tools, right? So you can take approaches and designs. You're not limited just by what the manufacturer of the geometry platform gives you. So, right. Got one more slide. Or next slide, please. Yeah, so I think for the engineering community, most people understand heat transfer, but we just wanted to include this just for the benefit of all. Because, fundamentally, there's several different heat transfer methods, 3 primary ones, right? That's conduction, right? And that's the transfer of heat energy by direct contact. Convection, where we actually move a fluid, or you have movement of heat by actual motion of fluids, right? And finally, we have radiation. It's the transfer of energy with the help of electromagnetic waves, right? Here on Earth, right, we're primarily focused on convection and conduction, right? And so for certain applications, especially in space where you don't have the benefit of an atmosphere, you have to rely on other methods like radiation often to transfer energy. For the focus of today, we're going to focus on conduction and convection. Go to our next slide. Then fundamentally, when we think about conduction and convection, we really need to think about surface area, right? By maximizing surface area, you're going to maximize your heat exchanger performance. And this is within reason, and because you're going to, the fundamental equations of heat transfer associated with convection and conduction are directly tied to surface area, and then the other one being wall thickness, right? And so fundamentally in nTop platform, we can use these math-based geometries that have incredibly high surface area to maximize performance. And that's kind of going to be the push, other general theme of the discussion today. So with that said, I'll turn this over to Mikey, where he's going to demonstrate some of these both in the software and also via presentation.
Thanks, Ryan. I will encourage a little bit at least to try and make this a bit interactive. So if you want to pop a couple comments or questions in chat, I may be able to answer those throughout the talk, but otherwise, as Jason alluded to, we'll do a lot of that or most of that towards the end. The first kind of example or study that we'll look at is this performance-driven design, where we're able to automate and parameterize the design of a heat exchanger to basically meet any performance requirements that that I want. So in this scenario, we'll presume that I have a company, or maybe as a design engineer, I sit around and create this basic configuration multiple times a day, or a handful of times throughout the week, where customer A will come at me and say, we want to have a heat exchanger meet these performance requirements given this design space, and then I'll give them a result. And what we can do is we can take your design objective, engineering equations, whatever they really are, and your primary design drivers, package those into a repeatable, re-executable workflow that will automatically recalculate and design your part based on on the needs that you're trying to meet or the performance you're trying to achieve from that. And before I take a moment to hop into the software, just to kind of help visualize what we're talking about, we'll go through a couple of little example problems here where let's assume that we want to meet a performance requirement of 23.5 kilowatts given a couple heat transfer coefficients going through the cold fluid domain here in blue or green, depending on your resolution, and then the hot fluid here in red. And we can design this heat exchanger. It meets these performance requirements, but then again, you know, it's never the same. Performance changes. Maybe we want to be more efficient, or maybe we find a way to increase the heat transfer coefficient by introducing some blowers. So we simply just change the values of the heat transfer coefficients for our two fluid domains. And again, the design recalculates and updates to meet that performance requirement of 23.5 kilowatts. But now maybe that design space has changed a little bit due to any number of parameters, but we can again change that ducting height. So now we've shrunk the heat exchanger, but it had to grow a little bit in width in order to accommodate the performance of 23.5 kilowatts. And the last thing, which I think is probably most exciting in this evolving field of especially these triply periodic minimal surfaces, is the studies that are being done on the different lattice types and the cell sizes of these lattices. So maybe studies get produced that say, you know, the gyroid is really good in certain scenarios, but the diamond lattice structure is typically better with heat exchangers of this configuration or these cell sizes. So again, we can quickly iterate and design for your performance based on whatever kind of requirements we need to meet or data that gets published. Again, it's just about, you know, being most efficient as an engineer, as a company, or whatever. So kind of with that, I think we've gotten a pretty good grasp of what this workflow looks like. But, you know, then we need to talk about, okay, cool, we're meeting our performance requirements, but at the same time, how does it look like when we're actually doing putting flow through there? What does that look like? Well, we can couple these designs with real-time simulation. And in this particular case, we used ANSYS Discovery Live. And so while we're continuing to meet these performance requirements, we can also get immediate feedback of what the solution is going to be like as far as you know, basic flow through these complex structures. And in just a matter of moments, you can get this feedback and see maybe we have some low pressure zones in the lattice, so we can kind of change the infill volume, or maybe at the top where we have this outlet, we have some recirculation, so we can change the ducting geometry a little bit to make the entire system more efficient, but at the same time continuing to meet those performance requirements. With that, I'm going to go ahead and hop into the software for just a couple moments here. I'm going to start off with a very basic example here, just to kind of let everyone get a grasp before I hop into that performance-driven design example we were looking at. So a very simple rectangular TPMS lattice structure on screen right now. And you can actually find a pretty detailed how-to video of this exact workflow that it's on screen now on our website. But basically all we do is create the lattice structure infill in whatever kind of geometry shape you have, whether it's going to be Cartesian, cylindrical, spherical. We have a TPMS that'll fit into each of those. And then from there, it's simply just extracting the fluid domains that fit inside these structures. And if you're not familiar with the triply periodic minimal surface, they're very unique structures in the sense that they allow the two fluid domains, in this case, to intermingle or mix very well. And a lot of shared surface area is between those two, which makes them very ideal for heat exchanger applications. And at the same time, you can kind of tell by their shape that they offer themselves for smooth flow topology. But you know, the more distance we travel as a particle of fluid through a heat exchanger, the more pressure drop we're going to experience, and the less efficient the whole structure is going to be. So what we can do, and this is part of, you know, a collective effort of engineers, is to try and characterize some of these shapes and aspect ratios. So if the flow is moving from right to left in this direction, maybe we want to stretch and morph the unit cell in the y-axis or the direction parallel to flow to try and reduce that pressure drop a little bit, but at the same time continuing to go well and above and beyond you know, traditional means of heat exchangers, so the shell and tube, for example. But once we've created that lattice structure and once we've created our fluid volumes, you know, you can look at this and say, man, Mike, these two fluids, they're going to mix. Oil is going to mix with my gas, or my water with whatever. But you know, with a couple of very simple steps, we can start to create these baffles that will you know, prevent these two fluids from mixing. So if I kind of hide the lattice structure, what we have here now are the baffles or barriers that we use to keep the two fluids from mixing, and that's just using a Boolean intersect with the fluid volume to create that barrier or baffle to keep the fluids from mixing. And then finally from there, it's just a matter of taking those baffles, unioning them to your initial structure, and then capping whatever ends you need to at the end to kind of make your final design or heat exchanger. So in this particular case, we have our cold fluid moving through, you know, front to back, and then our hot fluid moving left to right. Again, this is just a very simple example to kind of help, you know, allow everyone to get a grasp of where we're going to go and kind of how we can take a very simple concept and then start to morph that and turn it into you know, an actual engineering workflow that performs and does things for us that, you know, just previously weren't really accessible. And that's kind of what we're looking at now, is this performance-driven design heat exchanger. And so just to kind of take a moment to explain what this workflow looks like, and the design concept is hot air moves in through this bottom right duct, across the heat exchanger in the center, and out the back left. Cold fluid moves in through this back right, through the heat exchanger, and out the front left. And you can kind of see here already that we have the baffles created on both sides. So we're not going to get any mixing of these two fluids. And this particular example, while it's not you know, directly an aerospace example, this one is an HVAC concept. So it's a rather large heat exchanger as far as it goes. So we have a lot of surface area in this particular example, because we are trying to pull out, or you know, performances, in this case 23.5 kilowatts. But at the same time, maybe you know, I want to create a furnace that is a little bit larger and wants to and it needs to pull out a little bit more heat. I can just simply update my that parameter, and in just a few moments here, it takes just a few seconds, we'll see a new design pop up on screen of what it's going to look like. And while that's kind of rendering, the way it's done is we have these heat exchanger input parameters, And from that, we say, okay, what target surface area do we need to hit to meet those performance requirements? So we just kind of simply say, okay, this is my target surface area based on a cell size, a unit cell size of a TPMS structure, or in this case, just one gyroid. How much surface area do we have in this gyroid? And then we just kind of do a little bit of a back calculation to figure out how many of these unit cells we need to then hit our target surface area. And then from there, we just simply create an infill for that structure or that lattice structure to go in. And then that lattice structure gets created. And then it's just a matter of putting this lattice structure around your ductwork and combining the whole workflow together. So it looks complex, but it's amazingly simple and quite robust process in terms of how this whole system works. I'm going to turn the heat exchanger back on here. So, you know, after all is said and done, there's a lot of surface area that kind of gets cut away once we do some trimming of the corners, once we create our baffles, and once we do kind of our Boolean unions and blends and smoothing the radius to the ducting, we're going to lose a little bit of surface area. And at the very bottom here of the screen, we kind of have a surface area comparison and refinement section. And we can see that we have about a 1.2% difference from our target surface area to our final surface area. And this margin value has already been adjusted, but if this was at this percent difference would be a lot larger. But all we have to do then is come to this margin value, and we would adjust it based on what this this calculator output is. And so in this case, I'm just going to make it 0.6. And then again, it's going to just recalculate. It's going to go back to the beginning of the whole process and redesign to try and match your target surface area to what your final surface area is. Once again, you know, those baffles and other features of the heat exchanger were added into the whole system. So, you know, now we're a little bit closer. We're within 1% of our target surface area just by, you know, adding this margin variable into the design. And then finally, you know, meshing is kind of the next step as far as trying to get that into, in this particular case, into Discovery Live, just to kind of get an idea of what that flow is going to look like through this complex structure. And then it's just, you know, in this case, we just want to get this hot fluid domain meshed and then export it out as an STL in this case to then be voxelized and run in Discovery Live. I'm going to hop back into the slides here now. But again, it's quite powerful and really quite amazing what we have at our fingertips as engineers now. And this next example is more of a real world problem one, in the sense that we gave ourselves this objective of designing a fuel oil cooler that, again, we want to fit within a specific design space, but at the same time, we obviously want to improve the efficiency of it by, you know, either by also reducing part count, weight, etc. And this design inspiration for this fuel-cooled oil cooler came from an America Makes project, actually, that we saw a handful of years back, where they took a traditional shell and tube heat exchanger and applied additive manufacturing techniques to it to you know, look at viability of the AM process. And this was years ago. And so we said, let's see what we can do if we take this design concept or idea and apply a minimal surface lattice structure to that. And that's kind of what we did. So again, as Ryan mentioned, our primary drivers in a lot of our designs thus far have been surface area first, and then thickness, and that's, you know, directly proportional to the performance. And so, just to kind of describe what the idea or concept behind this design is, hot oil enters through the top, impinges on this blue dome, and moves around the outside, enters the red cylinder, which is you know, going to be a gyroid core eventually, and exits out the bottom. Hot fuel enters through this left port, comes up through that cylinder or the gyroid structure, and exits out the top right. And you can kind of see what the internal workings of that are there on the GIF on the right hand side. But then once we have that, then, you know, cool, it looks nice. Maybe I can print it. You know, we took manufacturing, additive manufacturing design methodologies into the original design, but is it going to work? How do I know it's going to meet my performance requirements, or how do I know it's going to be at least 25% better than the part I'm trying to replace? Well, you know, first and foremost, before we go to testing, which can be you know, time consuming, costly, we can do simulation. So we take those fluid volumes, the blue is the oil on the left here, and the blue is the fuel on the left, and the oil is this orange. We mesh these volumes in nTop, then we can export them into ANSYS to run our analysis. In particular case, we went through an ISIM CFD as an intermediate to a little bit of extra metric refinement at the time, and then ran the analysis and ANSYS CFX. And so the two contour plots that we see are the heat transfer coefficients on the fuel domain on the left, and then the oil domain on the right. And kind of one of the main things I wanted to just point out is at the bottom here of the fuel domain in the plenum, it's really red, right? So we have a lot of energy being sent into that plenum, a very high heat transfer coefficient down there. And so one of the first things we looked at is how can we direct more energy into the actual heat exchanger core, into that gyroid structure to improve the efficiency even more. And so just by manipulating the shape a little bit, we were able to not only introduce more energy into the core, but at the same time, we also met a lot of additional target markers and aided in additive manufacturing. So this original design concept is here on the left, and right away we can kind of see where we might have needed to add some supports for printing at the port, at the bottom of the shell, and even inside under the lattice structure. Turning your attention to the far right-hand side is the final solution that we landed on. So we've added a 45-degree cut to the shell. We did a revolved elliptical cut out of the gyroid hex structure, which allowed both of those to then become supportless structures for printing. The last thing that we added was more of a in the field performance-based design driver, and we added here a negative slope to this plenum so that the fuel in this case wouldn't pool at the bottom and either spontaneously combust or whatever and cause catastrophic failure. Whereas if you look at the original design on the left, all of this volume here under the port, that fuel would have just sat in a big pool and not really done anything or moved. But at the same time, then you could even argue that this would help your powder removal as far as you know, trying to get that out once the part is actually manufactured. The next little bit of design iterations that we looked at were at the surrounding the exit of the fuel from that heat exchanger core. Again, the original design is on the left, and in this particular case, we had circumferential vanes for that fuel to exit from. And then we kind of discovered, at least in this particular case, that if these vanes came out radially, we actually saw improved efficiency and flow overall. So just by adjusting a couple numbers, we're able to reshape this structure and simply just improve the overall efficiency that way. The last thing we looked at was trying to reduce these low pressure zones right above these exit ports here by simply just kind of pulling and morphing on those surfaces so that we try and create a smooth transition as the fuel exits out of that gyroid core. And then finally, you know, again, we need to do a final evaluation of that design. And so we simply just mesh those structures, bring them into ANSYS in this case, run your analysis, and then get your results. And while this GIF here on the left, it doesn't tell us a whole lot, we can kind of see how complex the fluid actually moves through these structures. But it just, for me, it helps to visualize and kind of get an idea of what's actually happening. But on the right is really the big takeaways in that the big takeaways are that heat transfer coefficient on both the fuel and oil domains. Finally, then comparing those two designs, the original concept on the left and final on the right. And the two areas I want to bring attention to are, again, that plenum at the bottom, where we have a lot of you know, wasted energy just being put into there as opposed to into the heat exchanger core itself. And then at the top where we have the that morphed geometry now, where we're able to manipulate very easily and change the shapes of complex structures to in this case aid in that transition of the fuel exiting from that core. And then, you know, let's print this and see how it looks. And so, as Ryan mentioned, we partnered up with HRL, who had developed a 7000 series aluminum, which had a very high yield strength. And that actually allowed us then to reduce the wall thickness by about half. So we have essentially then kind of redoubled our effectiveness, which before that, we actually had achieved a 140% increase in surface area when we compare this volume to a traditional shell and tube heat exchanger of that same size. But then when you couple that again with ANSYS or whatever kind of simulation package you have, there's going to be, you know, ideally an additional increase in efficiency or effectiveness based on your design iteration process, whether that's specifically to meet your performance or also try and hit manufacturing demands or criteria to make the part more printable or you know, make it fit into your overall design and hierarchy of you know, categorizing your parts and assemblies. But that is actually all I kind of have for you today. It was I feel like it was a lot to intake, so definitely feel free to pop some questions into the chat, and we'll be able to answer those as we see them, hopefully.
All right. Thank you, Mikey and Ryan. I will now head into the Q&A session. Once again, if you do have any questions for our presenters and you haven't done so already, please go ahead and type it into the chat box. Let's see. We do have a couple of questions here. So let's see. How thick were the walls?
In this design that we see on the screen, the walls are about 2 millimeters thick, I believe.
Okay. All right. Another here. Let's see. So this one says, "Hi, great presentation. How did your printed design compare to the pressure drop and heat transfer of the America Makes design?"
So we actually didn't have the actual America Makes design to do a comparison to, so we don't have a quantifiable numbers as far as that goes. But what we are in the process of doing right now is trying to quantify what the pressure drop is going to be across some of these structures. So let me take a moment here. So in this particular case, it's not this example that we're working on right now, but it's very akin to it in the sense that we have these cell sizes right here. And in this particular case, we're holding the cell size constant in the direction that is normal to flow, or in the X and Z axes. And in the Y axis, we want to kind of stretch that aspect ratio. And we're in the works of doing a study on that, as far as looking at how effective maybe, changing that aspect ratio and kind of stretching that shape out. And you can actually get a little bit of a glimpse of that. We're doing a talk next week, and we're going to touch on this a little bit as far as pressure drop goes.
All right, great. Let's see. Okay. What is the cost difference between an AM part and a traditional design?
I don't have a good answer for that. Maybe Ryan can pop in for that one.
So I think anytime you choose, if I was just to, in general, say if you're going to print a part versus maybe a tube and shell type design, I think the additive part, at least at small quantity, will likely be more expensive than the other part. We've been finding more and more, though, that there's oftentimes it often depends on how you quantify expense, right? And so expense could be lead time, right? So anytime you have a tube and shell or a copper based part, there's often a lot of brazing associated with that. And so oftentimes we've seen in programs where the brazing and the assembly and manufacture of that has led to long lead times, and then therefore has like delayed the program. So if you're delaying you're waiting on a $5,000 part and you're delaying a multi-million-dollar program, that might be something of concern to you. And so I think the key here is that anytime you choose an alternate manufacturing method like additive manufacturing, we need to, that might be a little bit higher cost. We need to justify the higher cost by increase in performance. And so there's a number of folks that we interact with and that are kind of pushing the boundaries of AM design. And so, another alternate classic use case too is that traditional design, it was prescribed to meet a particular volume under a prescriptive heat exchanger requirement. And oftentimes, at least in my Air Force career, the airplane itself doesn't change. It's often the avionics or electronics or other pieces that go into that aircraft that change. And now you need to be able to balance those new and additional heat loads, right? And so you might be volume constrained, and now you need to consider other approaches. So there's a lot of things that go into cost. That was like a long-winded way of saying it depends, right? So.
All right, thank you for that. All right, so okay, do you run into issues with powder removal for these printed designs?
It kind of depends, right? So the smaller your cell size, the more difficult you're going to have for removing the powder. And the more, like if you have a very serpentined path as far as, you know, adding, you know, this is already a serpentine path, but if we were going to add some extra geometry in here to have, you know, the flow kind of serpentine around these areas, then yes, there you would definitely have, you know, issues with removing all of the powder. But at the same time, I'm sure some techniques are going to come around as far as like aiding in powder removal, whether it's just kind of, you know, injecting some air in there initially to try and help jostle that around and get it out. But at the same time, what's going to kind of happen is we're going to develop guidelines, you know, as a collective engineering society. We're going to develop these guidelines as far as like, if you get to a cell size of this, if you get down to a cell size of too small, then, you know, it's not worth the effort to try and remove the powder. But at the same time, you can also argue at that small cell size, my pressure drop is going to be too high, so there's no reason to go down there anyway.
Thank you. All right, so the first heat exchanger design was the rectangular type. You know, okay, how much efficiency can be achieved in that design?
In this design, I presume. So, I mean, in this particular case, we're trying to, we're in this design, we're always going to meet performance, and that's what this repeatable workflow allows us to do. As far as comparing this to a traditional, let's say, furnace that you might have in your house or in your office building, we're not sure yet. But I can at least say, based on what we've done with the fuel cooled oil cooler, where we compared this same design space or volume to a traditional shell and tube heat exchanger, we saw 140% plus increase in surface area. So I would suspect that there would be a pretty substantial increase as far as efficiency with this design as well.
So we have a couple more questions here. All right, would having thin walls and ability to withstand high pressure while having high surface area have more effect on heat transfer than the actual conductivity of the metal material?
Let me reread that question.
Okay. Do you have that available to you over there? Or do you
yeah, I do see this one at least.
Okay. Okay.
I've only seen a couple.
So I think maybe, Mikey, if you go back to one of your slides with the heat transfer equation, and we're often simplifying a lot of this here, but in this case, the fundamental heat transfer equation here with Q is you're just balancing. There's a linear relationship between cross-sectional area and thickness, right? And so that you get to kind of choose which one you want to pick there in terms of increasing, at least this case, connectivity, right, across that surface. So most heat exchanger folks will want that to be as thin as possible, right? So you're minimizing T to fundament, and since we're dividing by the thickness, we're maximizing the conduction then. So I think there's always going to be a balance, and maybe early on too, we oversimplify the problem a little bit. In addition to surface area, you're always balancing pressure drop. So those are to calculate that pressure drop, though, it is not a simple equation, especially for these more complex geometries, and requires some additional analysis. So.
Thank you very much. Let me see. I want to make sure I get to all questions here. I don't want to miss anybody. We do a little bit of time today. Okay, so our last question, what should be the cell length and thickness for effectiveness?
What should be the cell length and thickness for effectiveness?
That's how the question was.
So that's obviously the most important thing that we need to try and discover, and is ultimately a very loaded question, because I don't think it's always going to be a one answer fits all as far as that goes. There probably will be some range, at least as far as geometry shapes go, with cell size and aspect ratio or wall thickness. As long as the smaller the thinner the wall, the more efficient the whole structure is going to be, as long as we're still meeting our structural requirements as far as pressure goes, right? So as far as wall thickness, I think it'll mostly come down to, once you've established your design from a structural standpoint, it'll come down to what material am I choosing, what machine is doing my printing, and therefore kind of what are my minimum feature sizes. So how small or how thin can I actually make my walls as far as manufacturing goes. On the cell size kind of side of it, it's going to come down to, and there are already studies coming out on cell sizes as far as pressure drop and effectiveness for, at least cylindrical geometries right now, and that's kind of what we're looking at. But what we saw pretty quickly, and we've just done a small study right now, but what we saw pretty fast is, let me do another cross section of this. And I'm going to put the cell size. So now I have my cell size here. It's equivalent 555 millimeters in each direction. And we saw a very substantial drop in pressure as soon as we increased our cell size by a factor of 2. We actually, it was quite remarkable. And so what we're kind of looking at now is, okay, let's maybe hover around an aspect ratio of 2 and kind of do a further deep dive into what this looks like. So again, it's not, I don't think, going to be a one size fits all scenario. But what we've seen initially so far is really any aspect ratio change in the direction of flow greatly impacts that pressure drop in.
And that, just on this point here, I think the key is that we're kind of at a super exciting time, right? Where we can manufacture what I call crazy geometry like this, right? This incredibly complex geometry, and then kind of coupled with the design pieces that we can design these things now. So not only can we manufacture, but now we can quickly design and iterate on these things, and we can answer some of these questions. And kind of to Mikey's point, where our intent is to demonstrate this in nTop platform, and then also be able to demonstrate that in tools that exist, at potential customers' sites, whether that's ANSYS or Abacus or whatever the simulation piece is. But and I think the reason that America Makes and Jason have invited us is that we're able to actually do all this together, right? And we're knocking down those barriers to performing those, not only the calculations, but then also coordinating those actual experiments to validate those. So very exciting times, and we look to be continue to be doing a lot of work in this area and answer some of these questions.
All right, great. All right. Once again, I'd like to thank Mike and Ryan. That'll wrap up today's TRX webinar series. If you have further questions for the presenters, please reach out to them directly. Do you guys have that last slide with your contact information in case anybody wants to reach out?
I actually Give me a second. I did not update it on this slide.
Okay, if you want to just go ahead and give your contact information, that'll work.
Yeah.
Or where they should reach out to.
I'm just going to put it on here real quick.
Okay, thank you very much. All right, while he's doing that, we'll be posting our survey going out to all those who participated. We do really appreciate the time that you take to provide America Makes feedback, so we may continue to improve and strengthen the additive community. And as a reminder that if you think you or your organization will be interested in sharing on the TRX webinar series, please fill out the form that follows the presentation, or you can reach out to myself, Jason Thomas, at jason.thomas@ncdmm.org.
Give me a second here. I lost the presenter
Okay,
mode.
no problem.
Cool.
All right. Okay, great. All right, so here are the two emails that you can reach out to Mikey and Ryan. Mikey and Ryan, thank you very much for your time today and for the great presentation. Everyone have a great day.
Thanks, Jason. Thanks, everyone.
Thanks, everybody.